In this section, we are going to be studying exponential and logarithmic equations, and we're going to be learning how to solve them. I want you to know that there are two types of exponential equations that we'll be learning how to solve today, and two types of logarithmic equations that we'll be solving in this section. One of the common student errors when we're solving exponential and logarithmic equations is students will confuse the two types of exponential or the two types of logarithmic equations when they're trying to solve. So let's just look at the exponential equations and just make sure that you understand the difference between the two types before I actually show you how to solve the two types. The first type of exponential equation is where the bases can be expressed as the same base. For example, 2 to the x is equal to 2 to the 5. That's a very basic example. Notice the bases on both sides of the equation are already the same. Another example would be 3 to the x equals 27. Now you may not think that these bases are the same right now, in which they're not, but they can be rewritten as the same because 27 is a power of 3. It's 3 cubed. So I can rewrite the equation with the same base. So both of these equations satisfy type 1, where the bases can be expressed as the same. Type 2 would be where the bases can not be expressed as the same base. For example, 3 to the x equals 26. Instead of 27, I use 26. We know 27 is 3 cubed, but 26 is not a power of 3. So I can't change 26 to be rewritten as the same base as the other side of the equation. So therefore this is of the type 2, where I could not do that. Just give you one more example. 2 to the x plus 1 equals 15. Notice 2 and 15 cannot be rewritten as the same base. 15 is not a power of 2, so I can't do that. So I'd have to use the methods described in type 2. Let's go through the steps of both, and then we'll give you some practice problems. For type 1, where the bases are the same, the first step is to change both expressions to be the same base. Sometimes you'll have to just change one side, sometimes you may have to change both sides, or sometimes they may already be the same base. But that's step 1. Step 2 says set the exponents equal to each other and solve. For our very simple example here, 2 to the x equals 2 to the 5. Well, if my bases are the same, then my exponents must then also be the same. So the answer to the first example is x equals 5. For our second example, 3 to the x equals 27, we have 3 to the x equals 3 to the 3. We had to rewrite it. Step 1, rewrite it with the same base. Step 2 says set the exponents equal to each other. So I'm going to look at these two exponents. Now that the bases are the same, I can set the exponents equal to each other, and my answer is x equals 3. So those two are very simple to solve. On type 2, where the bases cannot be expressed as the same base, we need to isolate the base with the variable exponent. Because the variable is on the base of 3, we need 3 to the x to be isolated. For example, if it said 7 plus 3 to the x, I'd have to subtract 7 from both sides to isolate the base. Step 2 says take the natural log of both sides of the equation. This will cause the variable in the exponent to move to the coefficient using the power rule. And lastly, we're going to solve for x. This steps take a little bit more space, so I'm not going to try to solve these two problems. I'm going to actually show you some more examples a little bit later. So let's focus on type 1, solving exponential equations with common bases. We call this the change of base solving method because we're going to be changing the bases to be the same. The property we just talked about is said if b to the m equals b to the n, the bases are the same, then the exponents must then be equal to each other, so the answer here would be m equals n. And that's the property that we're going to be using. So let's take a look at our first example. 4 to the x equals 16. I can rewrite 16 as a different base with the common base over here is 4. Normally we'd like to take the larger one and make it smaller. It's very difficult to try to take a smaller base and make it larger as possible. It just becomes a little cumbersome. So 16 can be rewritten as 4 squared. Are my two bases the same? Yes, they are. So I'm going to take my exponents and set them equal to each other. My answer is x equals 2. For our next problem, I still have a 16 here, so I'm going to try to reduce the 16 to a common base as the other side. Now we said 16 is 4 squared, didn't we? But the bases aren't the same. That didn't really help me very much. So what I'm going to do is erase the 4 squared and see if I can come up with another way of writing 16, but this time I really want to focus in on a power of 2. 2 raised to the what equals 16? Well, that's 2 to the 4. So now do I have my bases the same? Yes. So it's not just trying to rewrite 16 as a different base. It's rewriting 16 as the same base on the other side of the equation. On our first example, we had to rewrite it as 4 squared. But on our second example, we have 2 to the 4th. Both of those do multiply out to 16, but we used them differently because we needed to have different bases in each of those two problems. Now that I know that my bases are the same, I'm going to take my exponents and set them equal to each other, and that gets me 3x minus 8 is equal to 4. Now I can solve. Divide both sides by 3. X is equal to 4. You're always welcome to check your work. If you want to check your work, you would just replace 4 in every time you see an x and see if that does truly multiply to 16. We have 2 to the 12 minus 8. We're hoping that's 16. 2 to the 4, is that 16? Well, yes, it does check out. This is not a requirement, but if you'd like to check your work to see if you're doing it right, you're welcome to do that. For our next example, 27 to the x plus 3 equals 9 to the x minus 1, we have 27 and 9 as our two bases. In the previous two examples, all I had to do is rewrite one of the sides with a different base. But in this case, 27 can be rewritten as 3 cubed, 9 can be written as 3 squared, but I cannot write 27 as 9 to the something power. So it's easiest just to take it down to the smallest base that is common between them. In this case, we have 27 being 3 cubed, and 9 is 3 squared. So I've rewritten the base, but I still have to include the x plus 3 exponent and the x minus 1 exponent. Notice that I put these in parentheses. And the reason I put them in parentheses is because you changed the base to be 3 cubed. That means this 3 has to apply to both the x and the plus 3. Do I have the bases the same? Well, yes, I do. If the bases are the same, then I know that my exponents must also then be the same. And then I can distribute and solve my linear equation. I'm going to subtract 9. I'm also going to subtract 2x at the same time to get x is equal to negative 11. You're welcome to check your work. I'm not going to on this particular problem, but you're welcome to go back and check your work on any of the problems. The next two problems are very similar. The first one is a little bit more simple than the second one, and I did this on purpose. I wanted to make sure that you understand the first one so that when we go to the second one, that you truly understand what 1 over the square root of 3 can be rewritten as, which I know a lot of students have a hard time with. So let's look at our two bases that we have here. We have a base of 9, and we have a 1/3 on this side. So whenever I have a 1/3, the 3 is going to be my base, not necessarily the 1. So the base here I'm focusing in on as the 3, the value other than 1. Both 9 and 3 can be rewritten with a common base of 3. So 9 is going to be 3 squared. We still have the x. And 1/3 can be rewritten with a common base of 3 as 3 to the negative 1. This is one of those properties that we learned in intermediate algebra that you needed to know for this class. We reminded you in the beginning of this unit about some of those properties, and this is just one of those properties that keeps coming up this unit. So 1/3 can be rewritten as 3 to the negative 1. Are my two bases the same? Well, sure they are. Now that I've rewritten them as the same base, then the exponents then must also be equal to each other. So I have 2x is equal to negative 1. Solve my linear equation to get x is equal to negative 1/2. On my next problem, I have 9 as a base, and I also have a 3 as a base, but I've got this new square root problem. On the left-hand side, I'm still going to be 3 squared to the x. And on the right side, we've talked about how 1/3 is the same thing as 3 to the negative 1. But this time I'm working with the square root of 3. So I can rewrite this as the square root of 3 to the negative 1. And another one of those properties that we learned from intermediate algebra is how to rewrite radicals with an exponent. And the way I can rewrite this radical with an exponent is the invisible 1 exponent on the 3 over the invisible 2 in the index here, which means 3 to the 1/2. So 3 to the 1/2 is the square root of 3, but we're still being raised to the negative 1 power. So 1 over the square root of 3 is the same thing as 3. I'm going to multiply my exponents here to get negative 1/2. The negative tells me I moved downstairs. The 1/2 says I'm a square root. So 1 over the square root of 3 can be rewritten as 3 to the negative 1/2. Are my bases the same? Well, certainly they are. If my bases are the same, then I'm going to set my two exponents equal to each other and solve. Divide both sides by 2. X is equal to negative 1/4.